Once a radiotherapy beam is delivered to the patient, the radiation dose cannot be removed. It is very important that both the quantity and position of the radiation beam be correct for radiotherapy to succeed. To ensure the radiotherapy beam is placed at the correct location on the patient, some form of imaging is needed. In this lesson, we will discuss technologies that are used to image the patient at the time of radiotherapy to ensure the correct beam positioning during treatment. Target volumes in radiotherapy are defined by three terms: the GTV, or gross tumor volume, the CTV, or clinical target volume, and the PTV, which is the planning target volume. Each one of these represents a location where tumor cells may be present. For radiotherapy to succeed, it is critical that all cells be part of the treated volume. The definition of radiotherapy treatment volumes was established by the ICRU, the International Commission on Radiological Units. This was done in 3 publications between 1990 and 2011. The volumes defined by the ICRU are the GTV, which stands for gross tumor volume. This includes the bulk tissue of the tumor. The CTV is the clinical target volume, and this includes microscopic disease and spread of the tumor. The ITV, or integrated target volume, was added recently, and this accounts for tumor movement. The PTV, or planning target volume, includes beam positioning errors at the time of treatment. In this slide, we see the concepts of the GTV, CTV, and PTV in terms of patient anatomy. The CTV extends beyond the gross area where bulk tumor is present and includes directions of tumor spread. The PTV includes a margin around the CTV to allow for errors in how the patient is positioned relative to the placement of the radiotherapy beam. Placing the radiotherapy beam at the correct location is one of the most important problems for radiotherapy. The ICRU 50, 62, and 83 guidelines established the concepts of GTV, CTV, and PTV. The GTV and CTV are determined by the disease, its stage, and how tumor cells naturally spread. It's a patient factor and cannot be changed before treatment. The PTV, on the other hand, is a problem of locating the tumor and placing a radiotherapy beam at the position that was determined. It is largely a technology problem, and the PTV can be changed by utilizing advanced means of localizing the tumor at the time of treatment and then placing the radiotherapy beam accordingly. However, even with good imaging technology, the radiotherapy beam positioning problem is challenging because tumor tissues are soft tissues, which are similar to healthy tissues, and difficult to visualize using X-rays. In radiotherapy practice, several solutions have been implemented for image guidance. These are both X-ray and MRI based. The X-ray based systems use a high energy beam, which is convenient, but does not produce high quality images. Kilovoltage beam produces better images, but require additional systems to the linear accelerator. MRI systems offer improved ability to visualize and locate tumor tissues, but are quite complicated to integrate with linear accelerators. The most convenient and straightforward means of creating an image of the radiotherapy beam location with the tumor is to use the radiotherapy beam itself to create an image. In this case, it is required to image an area just larger than the radiotherapy portal, and then add an additional beam with just a treatment beam to see if it covers the required tissues. The original systems used film or film screen technology to record the image. However, they were replaced with electronic systems that were both more convenient and could also improve image quality. 3 types of electronic systems have been used: a fluorescent screen with mirror and video camera system, an array of liquid ion chambers, and finally a system consisting of amorphous silicon detectors. This picture shows the position of the megavoltage or MV detector, as it is known, as well as some of the configurations that have been used in commercial systems. It deploys directly in the beam, distal to the patient. On the bottom left is a fluorescent screen and video camera system, which was housed in a light-proof, bellows-mounted chamber. The system suffered from noise due to the stray light and poor detector efficiency, which is a combination of both the screen and camera. Efforts were made to improve this using fiber optic pipes, as shown on the bottom right, but these systems were nevertheless replaced with more efficient systems. Liquid ion chamber systems, as shown in the bottom middle, significantly improved image quality and were also able to be used as dosimeters, allowing the detector to be used to measure patient exit dosimetry. These systems were also eventually replaced with amorphous silicon detector systems, which are fully solid state, low noise, and high imaging efficiency, which means high detector quantum efficiency, and are fully digital. These are the standard MV imaging devices sold commercially today. Due to the predominant Compton scattering at MV beam energies, MV portal imaging systems suffered from poor image quality. The device shown on this slide is an imaging phantom known as a Las Vegas phantom, which was made of aluminum and had holes of various widths and depths drilled into it. The darkened holes in the middle slide were considered to be detectable with a well-performing system, but the latter holes were considered to be too difficult to image with this technique. The image on the right shows a reasonably good quality image of the Las Vegas phantom detector using an MV system. The poor image quality associated with MV imaging is primarily due to the poor contrast due to the predominance of Compton scattering, which takes place at megavoltage energies. For such images, there is no strong dependence on atomic number Z, and therefore very little of the differential absorption seen in diagnostic radiology. In the MV range, Compton interactions dominate, and the probability of a Compton interaction is proportional to the electron density in the material, which is roughly independent of the atomic number Z. In the KV range, a photoelectric interaction dominates, which have a Z-cube dependence, and so there is a greater image contrast between tissues that have a large difference in atomic number, such as bone or air, which is in lungs, and soft tissues. These images are examples of radiographs of the same object taken with KV and MV imaging. The contrast due to the bony anatomy at KV energies is clearly better than that of the MV energies. To benefit from KV imaging, linear accelerators must have components added to them to create the needed lower energy beam where image contrast will depend on the atomic number Z to the third power. The means by which the KV imaging systems have been added to linear accelerators is to place the KV beam orthogonal to the MV beam. This figure shows a KV imaging system added to a C-arm style linear accelerator. It is mounted orthogonally to the MV beam. Because it is not coincident with the MV beam, the linear accelerator must be rotated 90 degrees to first create the KV image. The unit is then counter-rotated so the MV beam is located where the KV beam was for the verification image, and the beam position can be verified. It is important in this process to ensure geometric stability of the KV-MV alignment so that the KV image represents the true location of the tissues relative to the MV beam. Planar X-ray imaging can produce images with a good bony anatomy contrast. Significant contrast improvements can be achieved by using the same KV beam to create a tomographic image. A tomographic image is one where image projections are back projected, filtered, and then reconstructed to create a tomographic image slice in the subject. This process can increase subject image contrast significantly, on the order of several orders of magnitude. As well as doing this on the linear accelerator just prior to radiotherapy treatment, we can create a high energy image that can be compared to the treatment planning CT image to ensure that the treatment beam is placed where it was planned to be positioned. The KV systems on linear accelerators, when rotated and imaging at the same time, produce a cone beam image set which can be reconstructed to create a 3D image. The accelerator system must be rotated at speeds that are much slower than for a diagnostic CT machine, speeds of around 1 revolution per minute, which can cause motion artifacts. As well, the detectors used for linear accelerator-based cone beam systems, or CBCT, do not have certain scatter reduction features used in diagnostic units. For these two reasons, CBCT systems do not have as high an image quality as diagnostic CT systems, but they nevertheless have much superior contrast than planar X-ray imaging systems. This slide shows a planning CT image superimposed on the treatment CBCT image. The software allows the images to be viewed simultaneously so that the placement of the subject or patient relative to a fixed reference point, such as the Linux isocenter or center of rotation, can be evaluated, and then the beam position relative to an important portions of the image, such as the PTV, can be measured. If the beam position needs to be translated because it does not match with the desired PTV, then this can be done before the treatment beam is applied. This slide shows the imaging components and their arrangements on a Varian linear accelerator. This slide shows the megavoltage imaging components and their arrangements on an Electa linear accelerator. This slide shows the kilovoltage imaging components and their arrangement on an Electa linear accelerator. The X-ray-based image guidance systems for radiotherapy are natural systems to use on Linux, even the added Phys systems. These have been used for about 15 years now and are considered standard features on modern linear accelerators. X-ray-based systems are limited, however, since they have the limited ability to provide soft tissue contrast between a tumor and other tissues without cancer. MRI is ideally suited to image cancer due to the way MRI creates images. Unlike X-rays, MRI creates images by measuring the nuclear magnetic resonance of atoms in a subject, which are usually hydrogen nuclei. It uses a strong magnetic field to align the nuclear magnetic moments in the subject. It then disturbs the magnetic moments using an RF pulse. The time for the nuclear magnetic moments to return to the aligned state depends on the magnetic field in the subject, as well as tissue properties. It is highly dependent on how water in the tissues are organized. Water is organized differently in cancer tissues than in healthy tissues, and so cancer can be readily visualized using MRI imaging. In the rest of this lesson, we will explain the technical challenges associated with MRI linear accelerator integration. We will also summarize the solutions that are actively being pursued worldwide and discuss the problems of radiation dosimetry in a magnetic field. As we have discussed in previous lessons, linear accelerators consist of a high-energy electron beam that is created by injecting high-power microwaves into a waveguide that is capable of creating electric fields that can accelerate injected electrons to high energies. It has beam optic systems that are magnetically based, as well as mechanical systems to collimate the photon beam. An MRI is very different than a linear accelerator. It uses a large magnetic coil that surrounds the patient to create a magnetic field. It also has accessories, gradient coils and RF coils, that are used to create the subject images. MRI needs a very high magnetic field to create a sufficiently large population of aligned nuclear magnetic moments, or of atoms in a subject. It also has what are called gradient magnets to encode the image space, as well as RF transmission coils and receive coils to generate a pulse that perturbs the nuclear magnetic moment in the subject, and then listens to the echoes created by these moments as they return to their equilibrium position. The images are created by the dynamics of the decay times associated with the return of the nuclear magnetic moments to equilibrium. There are two principal means of decay, and these are referred to as T1 and T2 decays. The requirements on the components of the MRI are quite stringent, where we are looking for a very homogeneous region of magnetic field, as well as very linear gradient magnets and a powerful RF transmission coils. Linear accelerators and MRI units are not very compatible. It is difficult to imagine a geometry where the two systems can coexist and not mechanically interfere with each other. Linear accelerators are high-powered devices that produce very high-energy particles that need open access to the patient. MRI systems surround the patient and produce exquisite images of soft tissues based on a few signal sources producing small signals. There are several sources of interference that make integrating a linear accelerator and MRI difficult. Firstly, there is the issue of linear accelerator access to a patient that is enclosed by an MRI. Secondly, the magnetic field of the MRI will affect the electron acceleration process, since the magnetic field will alter the electron path by the Lorentz force F equals QV cross B. The magnetic field of the MRI also affects the dose distribution in the patient, since the scattered electrons that are created when the photon beam irradiates the patient will also be affected by the magnetic field, which will change the dose distribution. Finally, the linear accelerator is a source of RF noise that will affect the MR images, forming signal read by the receiver RF coils. This slide shows the interaction of a moving electron beam with a magnetic field, where the electron path will become circular when entering a perpendicular magnetic field. The radius of curvature of the electron path depends on both the electron energy as well as the magnetic field strength. This graph shows the relationship. Lower magnetic fields at large electron energies have the largest radius of curvature, which corresponds to the smallest change in its linear path. Small electron energies with a large magnetic field have a very small radius of curvature, meaning that their path has changed considerably. Linear accelerators are also sources of RF noise. The power between the magnetron and most MRI Linux systems use magnetrons, and the PFN can be reflected at frequencies that are not impedance matched during the rise and fall of the high current pulse. This causes oscillations in the line between the PFN and the load. This graph shows measurements of noise from a magnetron modulator up to 400 MHz. Three types of MRI Linux systems have been developed with the intention of creating a commercially available system. They were by the Universities of Florida, the University of Utrecht, and the University of Alberta. ViewRay is a company formed at the University of Florida. Its first product used cobalt irradiators instead of a linear accelerator to avoid many of the compatibility issues between linear accelerators and MRI units. This approach eliminates the magnetic field interaction with the charged particle acceleration process. However, there are some compatibility issues since cobalt is ferromagnetic. However, these issues can be addressed by magnetic shielding. It used 3 cobalt sources to improve dose rate and had a low field MRI which operated at 0.35 Tesla. The second generation ViewRay systems utilize a linear accelerator as the radiation source and has a clever means of RF isolation. This slide shows the layout of the first generation Renaissance ViewRay system and the second generation Meridian system. This slide shows the details of the RF isolation system and how the MRI magnet is split into 2 portions to allow the linear accelerators to point at the patient through the opening of the split magnet system. The University of Utrecht used a similar approach as ViewRay in terms of overall geometry. It uses a higher magnetic field at 1.5 Tesla, which is considered a diagnostic grade MRI system. The University of Utrecht approach used linear accelerators from the very beginning. It split the MRI magnet into 2 and used a spacer to hold the 2 magnet portions in place so that the X-ray beam could irradiate between the split solenoid magnet. It achieved a reasonably large 40 by 30 cm imaging zone and employed active magnetic shielding of the linear accelerator. It also used an innovative approach to the RF shield where the bore of the MRI unit became part of the RF cage. This diagram shows a schematic of the split MRI magnet and placement of the linear accelerator. The magnetic field of the MRI is also shown, showing where it is reduced, where the linear accelerator will be placed in order to avoid magnetic interference. This diagram shows an early experimental setup of the University of Utrecht system. The MRI is in the background, and the linear accelerator components in the foreground. The accelerated waveguide itself is not shown. This slide shows the first images taken and published by the University of Utrecht group, showing a subject imaged with radiation and without radiation. The University of Utrecht approach has been commercialized by Elekta, which is one of the major linear accelerator manufacturers. This diagram, provided by Elekta, shows the linear accelerator placement on a larger gantry surrounding the MRI bore. The third system described in this lesson was developed at the University of Alberta. It uses a bipolar, which is an open MRI system. The first systems pointed the linear accelerator in between poles. Later systems pointed the linear accelerator through the poles, aligning the linear accelerator with the magnetic field of the poles. It uses a relatively low MRI magnetic field of 0.6 Tesla. It decouples the MRI from the linear accelerator by passive magnetic shielding. When the linear accelerator is positioned in line to the MRI magnetic field, this effectively removes the magnetic interference between the 2 devices. This slide shows the first prototype MRI magnet and integrated system for the University of Alberta system. The linear accelerator is positioned in between the MRI poles, removing the mechanical interference between the 2 devices. This requires the 2 components to rotate together when the linear accelerator is rotated around the patient. The RF interference in the University of Alberta system is achieved by separating the microwave power source and modulator from the MRI and accelerator system and placing an RF isolation cage in between. The University of Alberta system was adapted to exploit a different linear accelerator geometry where magnetic interference is not problematic. Many linear accelerators require an axial magnetic field to keep accelerating electrons axially focused. Traveling wave accelerators are dependent on this focusing mechanism, as well as accelerators using the energy switch. The University of Alberta system exploits this mechanism in order to bring the linear accelerator and MRI in close proximity with each other and not suffer from magnetic interference. The mechanism of magnetic focusing relies on both the radial and axial components of a solenoid magnetic field. An electron moving in parallel direction to the axial magnetic field will be deflected by the magnetic field's radial component. The radial component is not drawn in this diagram. The resulting circular motion will then be affected by the axial component of the magnetic field, which causes a focusing force. This focusing property of axial magnetic fields applies to electron motion in an accelerator, as well as to the electron motion in a material resulting from photon interactions. This effect was demonstrated in this paper using Monte Carlo calculations. The University of Alberta system exploits this focusing effect of longitudinal magnetic fields by placing a linear accelerator centrally in a bipolar MRI magnet. With the linear accelerator pointed along the central axis of the magnetic poles, this effectively removes the magnetic interference between the devices. This diagram shows the prototype assembly drawing, as well as the gantry and bipolar magnets mounted in this gantry. The first images of a subject with and without radiation from the University of Alberta system were published in 2009. More recent clinical images showing the image quality is also shown in this figure on the right. The University of Alberta system is being commercialized by a company called Magnet TX, which is based in Edmonton. One of the issues with MRI linear accelerator integration is the effect of the MRI on the dose delivered to the patient. Dose is delivered not by the photons themselves, but by the electrons that are created by the high-energy photon beam. These electrons are scattered in the patient, and since the patient is placed in a strong magnetic field, the motion of the scattered electrons will be altered by the presence of the magnetic field. This diagram shows a dose kernel, which is the sum of the energy released by an incident photon, as well as its geometric shape. It's composed of the primary scattered electron, as well as scattered photons, secondary Brown-Thurling photons, and secondary scattered electrons. The dose kernel, like Brown-Thurling radiation, is forward-directed. When a dose kernel is convolved and superposed with the total energy released by a photon beam, the result is the dose distribution in the subject. Because the dose kernel is largely composed of scattered electrons, the dose kernel is significantly changed by the presence of a magnetic field, as shown in this 2007 publication. The effect of the magnetic field on the dose distribution can be significant. In this diagram, a single photon beam is incident on a water tank type of phantom with a perpendicular magnetic field. The effect is to displace the dose distribution in a direction that is transverse to the photon beam. The diagram also shown what is called the electron return effect, where exit electrons are returned to the phantom by the magnetic field, depositing dose there. This diagram shows the dose distribution changes for a parallel opposed dose distribution in a system like the ones of ViewRay or Electa, where the magnetic field does not rotate with the radiation beam. The parallel opposed pair is a fairly common beam arrangement in radiotherapy. Due to the rotation of the beam by static magnetic field, the shifts of dose distribution are fairly complex, resulting in a dose distribution that is not shifted, but has noticeable dose differences at material interfaces, such as water to lung, as well as at the beam edges. For the method used by the University of Alberta, where the electron motion is largely parallel to the magnetic field, the dose distribution changes are much smaller and can be neglected for the 0.6 Tesla magnetic field employed in that system. To conclude the MRI linear accelerator integration discussion, there are important difficulties in integrating the two devices since the systems are quite dissimilar. There is both magnetic and RF interference. Both types of interference can be removed through shielding. Two approaches have been tried with commercially available systems, one where the magnetic field and the linear accelerator are placed perpendicular, and one where they are placed in parallel. For the perpendicular systems, there are also effects on dose distribution in the patient, but these effects are not present for the systems where the magnetic field and linear accelerator are placed in parallel.